In this chapter, we will learn how to generate our own artificial dataset. But first, of course, why would we want to do this? Well, the reason is twofold. The first reason is the observation that every dataset is unique, in the sense that every dataset comes with its own peculiarities and its own specifications that depend on the context of the data problem that you're working with. For instance, you could have outliers that are either very important or not important at all, and you might have invalid values that you need to take care of. And because I want all of the ideas and concepts that we will learn about statistics in this course, and even the code that we will see, to be applicable to your own specific data problem, I thought it was best to demonstrate all of these on the most general dataset. And generating our own dataset allows us to do that. The second reason why we would want to generate our own artificial datasets is because it allows us to tweak datasets to serve our specific educational purposes. For instance, when we look at the p-value or correlation, we can generate datasets that are specifically fine-tuned to illustrate these concepts and thereby make them more visual and thus more intuitive. For example, to study correlation, we can generate a lot of different datasets which are all equal except for the measure of correlation. And thereby we are not limited to a real-life dataset, which then of course only has one measure of correlation. So how do we then generate an artificial dataset? Well, a dataset is basically a bunch of random numbers, but not just any random numbers. As we've seen in the previous chapter, if we bring these random numbers together to form their histogram, they should exhibit an emergent or aggregate pattern. For instance, the shape of the histogram of a normal distribution should have this bell-shaped curve. How do we now use Python to bring together these two components? Generating random numbers, which, if brought together, exhibit a general emergent pattern. And it turns out that Python allows us to do this with just one line of code and 3 numbers. So let's dive into the code and see how this is done. In this first line of code, we define the number of observations or the number of data points that we want to have in our artificial dataset. In our case, we choose 100,000 data points and we assign it to npop. Now, this pop comes from population, and we will shortly see why we use this terminology. Then in the second line, we actually generate the artificial dataset and we assign it to a Python array. To do so, we type numpy.random, which generates the random numbers, and we add .normal. Now this .normal takes care of the requirement that when we take all of these random numbers together to make their histogram, the shape of this histogram will be the shape of a normal distribution. Remember this bell-shaped curve. Now, as we saw in the previous chapter, a normal distribution basically has 2 parameters that define its shape. The first one is the mean of the distribution, which shifts the bell-shaped curve along the x-axis. The second parameter is the broadness parameter, which determines how clustered around the mean our observations lie. It can be even very broad or it can be very peaked. And therefore we provide this .normal function with these parameters. We have the location is equal to 1, which is the mean of our distribution, and we have the scale to be equal 0.5, which indicates the broadness of our distribution. The third parameter in this function is the size parameter, which basically means how many numbers that we want to generate according to these specifications. And of course, this will be npop, our 100,000 artificial data points. And thus, it is this single line of code that generates 100,000 random numbers, which are nonetheless distributed according to a normal distribution. A normal distribution with a mean of 1 and a standard deviation of 0.5. And we generate 2 of these artificial datasets just to compare the two and see how these parameters influence the shape of their histogram. Now, to see the shape of their histogram, we need of course to visualize the histogram of these random datasets, because at this point they are still contained within the Python array, meaning we now have 2 arrays with 100,000 random numbers each, so we want to visualize them in a histogram. Before we continue, a quick reminder. During these course lectures, I will not go into detail for every line of code. This would take me way too long and detract from the core message of each lesson. Now, if you do want to have this information, I separately recorded videos where I indeed go through each line of code explaining what it does. I uploaded them separately onto the YouTube channel Code for Data Science, which you can find through a quick search or in the course materials. So let's get back to the lecture. And now we want to visualize the histograms for our two generated datasets. And to do so, the first step will be to define the figure and the axis. Now, in our case, this will be a subplot because we want to bring different visualizations together inside the same figure. And then the plotting of the histogram itself is done in line 16 of this code. We take the axis on which we want to visualize this histogram and we add .hist. Now the .hist function takes in all of the parameters that we want to give to our histogram visualization. The first one is of course the data. In our case, our data is a Python array with 100,000 randomly generated numbers. Then we choose the number of bins to be 30, and then we set density to true. Now, in a second, I will come back to this density parameter, which is very important. And the rest of the parameters are all layout parameters. The color of the bars, the edge color, and so on and so on. We do the same for our population too, which we will plot on the same axis, so on the same figure, so that we can compare the two. We set a title, and then we add a legend to this plot, such that we can distinguish between population 1 and population 2. Now this legend, in fact, takes the label parameter of each visualization. In this case, population 1 for the first one, and population 2 for our second histogram. So you can run this cell, and then we can see that indeed we get a histogram here on the left-hand side. We indeed see that we have a normal distribution, so both populations have this bell-shaped curve, and we see that indeed population 1 is centered around the value 1, and population 2 is shifted a slight bit to the right and is centered around 1.5. Now this reflects the fact that we chose our locations for our two populations to be 1 for the first one and 1.5 for the second one. Now the broadness of both distributions are equal to each other because we made it so. Now before we go on, I want to make a remark on the numbers on the vertical axis here, on the y-axis. Because for histograms, you probably expected there to be a very large number here because they would correspond to the number of observations to each data bin. And because we had 100,000 observations, we would have expected a very large number here. And in fact, we can get a very large number here if we put this density parameter inside of our histogram equal to false instead of true. And if we do this and we run this cell again, then we see that we indeed have these large numbers on our y-axis. For instance, if we look at the largest bin in our histogram, we see that it corresponds to roughly 11,000. So 11,000 of our 100,000 generated data points will fall within this mostly populated bin. Now, why would we want to have this parameter defined as true? Well, the reason is twofold. So let me put it back to true and run the cell again. And we again have this largest number of 0.8. So the two reasons why we would want to have this y-axis over the previous one is twofold. The first reason is that this y-axis, these numbers, don't change if we change the number of bins. If we again go to the definition of our histogram and we change the number of bins to, let's say, 60, so we double the amount of bins, we see that the y-axis didn't change at all. Now, if you remember the animation that we have where we doubled the amount of bins of our histogram in the previous chapter, then there we saw that the y-axis indeed halved each doubling step. And this isn't the case if we put this density parameter to true. So let me then again put the number of bins equal to 30. And of course, the number on the y-axis didn't change. The second reason is that in later chapters, we will look at the probability density function in more detail. And there, we want to visualize the histogram and its approximate probability density function on the same figure. Now, to do this, we need to take into account that the probability density function had this peculiar property, namely that the area under the curve was equal to 1. Now, this comes back to the fact that the probability density function represents the probability of finding a specific observation, and the probability of finding any observation is equal to 1. To make this concrete, a simple example. A coin flip can have heads 50% of the time and tails 50% of the time. So these two add up to 100%. Now the coin can also be biased. For instance, it comes up head 70% of the times, but that means that it will come up tails 30% of the time. So all of the possible outcomes, head or tails, taken together have to add up to 100% of the times. And that is why the area under the curve of the probability density function has to be equal to 1. Now, if we then, coming back to our histogram, want to plot the probability density function on the same figure as our histogram, that means that our histogram also needs to have an area of equal to 1. Now, to do this, of course, we need to add up the surface of each individual bar of our histogram. And the surface of each bar is the surface of a rectangle. So in our histogram here, if we multiply each width of a bar with the height of a bar, and then we add all of them together for the entire histogram, we would get a total sum of 1. And that is exactly what this y-axis allows us to do, because the y-axis determines the height of the bar. And that, in a nutshell, is why we will, throughout this course, choose the density parameter in the histogram function to be equal to true. Now, there is a lot more code in this cell. And in fact, in the next lesson, we will explain this code and use it to see how generating datasets, as we did in this lesson, simulates a real-life scenario for a data scientist and get to the heart of statistics.